Okay, welcome back to the class, and we have been discussing this hard decoding, how this hard decoding actually reduces to the nearest distance likelihood rule, okay. Plus I will use this framework to develop soft decoding, okay. Before we wrap this up, a quick recap of what we have done till now, okay. So we have considered this abstracted transmitter and an abstracted receiver and our AWGN channel, okay. So if you recall, this transmitter takes a message signal, maps it to some QAM constellation, this QAM constellation is transmitted over AWGN channel, and then receiver receives this received signal R, okay, and then based on this received signal it has to come up with this estimate of M, okay, right. And how this estimate of M is calculated in our case is basically looking at the map rule, okay. And what is this map rule? What does it tell? It estimates the estimate of M is chosen as M0 if this probability, okay, which is the A posterior probability, is greater than this A posterior probability, okay. And what is this A posterior probability? Basically the posterior probability of rho given M naught, okay, into the probability of M naught, okay, right. So now what this reduces to is as follows, okay. That's what we calculated in the last class, that this PDF of the received signal is the PDF of the noise, and which is shifted by S naught given M naught was transmitted, okay. And then on right side similarly we have shifted PDF of noise shifted by S1 and then scaled by P of M1, okay. And what is this? Now this is a PDF of noise shifted by S naught, PDF of noise shifted by S1, okay, right. Now using this we will basically analyze few things, and what are we going to analyze, okay. So I am going to consider multiple examples, okay, and then see how that map varies, okay, how does that map rule change. So what are we saying, okay, when S naught is 1, okay, what are we saying, that S naught of 1 is transmitted with a probability of 0.7, okay. Recall that we are considering binary phase shift key, okay. So there will be only two values, M0 and M1, okay, right. And so we are transmitting S0 is 1, and what is the other value? -1, and that is being transmitted with a probability of 0.3, okay, correct. And now if you look at it, okay, so we have to consider the noise variance sigma square. So this is the noise power, and considering for simplicity as 1, okay. What is happening now is, okay, so if you look at those like the probabilities which we looked at in the last slide, okay, what were they, okay. So if I have them here, okay, no, okay, so I'll have to go back a little bit, okay. But what is this? Okay, this is PDF of a Gaussian, correct, okay. And you look at this, what is this? Scaled by a priori probability of message M naught being transmitted, okay. Similarly, this is a PDF of another Gaussian, okay, and then basically scaled by a priori probability of M1. So what am I going to do in the next slide, which I showed you just now? I am going to plot both of them, okay. Plot this PDF scaled by this probability, plot this PDF scaled by this probability, and I just showed you, right, we know everything from here, okay. We know noise variance, we know P of M naught, we know what S naught is, right, okay. Then it is very easy to plot this PDF scaled by this constant number. It is very easy to plot this PDF and scale by this constant number, correct, okay, right. So if you look at the plot in the next slide, that is what is happening. How many such PDFs are there? There are two PDFs, okay, one on the left hand side and one on the right hand side, okay. And so what is this PDF in blue, okay, where is it located? It is located at S1, which is -1, right. This is a blue PDF, okay. And why this blue PDF has a lower height than the PDF in red? Because this is scaled by 0.3, right. This blue PDF, what is the a priori probability? It is 0.3, right. correct? And otherwise the PDF will be at 1 if it is not scaled. Okay, P of M0 is basically, if both of them are like, if it is not scaled PDF, it has to, its value, its peak will be at 1. Now we are scaling it with probability 0.3, so you see this, it is reduced to, the height is reduced to 0.3. In this case, it is scaled by 0.7, so the height is 0.7, right? The PDF, the red PDF is at value, the height it is at 0.7, okay, right, okay. Now, so this is what is sitting on the right side, and this is one PDF and this is another PDF. Now what do we need to calculate? Okay, what does basically the map rule says? When will you pick m hat as m naught? Okay, m naught is basically this s naught. Okay, when will you pick this? When the probability in red is greater than probability in blue, right? Okay, so what's happening? Okay, if you look at this, this is basically the first PDF, okay, and this is the second PDF, okay. Now what is happening here? So these two PDFs intersect at certain value, okay, I am calling this value as A, okay, and whenever they intersect, wherever they intersect, that value is, the probability is same, of course, right, that is basically this, they are intersecting and that value will be same, okay, wherever they are intersecting. Now on this side, okay, this intersection point, I am calling it as a threshold A. Okay, right? So what are we saying here? On this side of threshold, what is happening? This PDF has a lower value than this PDF, right? You look at this. What is happening to this blue PDF on this side has a lower value than the red PDF, correct? On this side of the threshold, what is happening, right? That this blue PDF has a higher value than the red PDF, correct? Right? So, and what was the rule? So what is this rule? Whenever this probability is greater, rho given S naught into P of M naught is greater, what will you declare? The estimate of message will become M naught. And where is it happening? It is happening on this side of the threshold, okay. So this is basically becoming the threshold, okay. So if this received value is greater than this threshold, what does that mean? Okay, that this PDF is greater. Then what will happen? If this PDF is greater, which message was transmitted? M0, right? M is equal to, declare m hat as M0 if the received value rho is greater than A. And it is essentially the same what we saw on the last slide, okay? That probability of, this is that scaled PDF, look at this, right? P of n rho minus, what is this? S naught given M naught. And if this value is greater than P of rho minus S1 into P of M1, you declare the transmit signal as M0. And where is that happening? As I said, it is happening on this side of the threshold, okay, right? So if rho is greater than A, M hat becomes M naught, okay. So now to calculate this threshold, you should know this threshold, where to like basically declare this, right? If rho is greater than A, you have to calculate this threshold, okay. And how will you calculate this threshold? Both these PDFs are equal, correct, okay. And if you calculate this, so what are we saying? On this threshold, both these PDFs are equal, so I have said that instead of inequality, I have made that equality, okay. And if you solve this, okay, right, so what have I said? Okay, at this value, what is rho? Rho is basically A, right. So what have I done here? I have taken those last equation, okay, P of, it was rho minus S naught square, but wherever we are calculating a threshold, rho is basically we are treating that as A. So rho has become A minus S naught. This is the PDF 1 by root 2 pi sigma square, that gets cancelled on both sides, and then we have P of M0, okay. So if you solve this, this is the threshold which we are going to get, okay, right. So I am not solving this is one step exercise which can be done very easily, okay. Now you see this, okay, this will immediately tell you how this map is basically equivalent to nearest distance rule, okay. Just to make our life simple, what are we doing here? I am setting P of M1 is equal to P of M0, okay. So what happens here? Ln of 1 is 0, so this term goes to 0, correct. What will this threshold be? S0 is 1 and S1 is minus 1, this threshold will be 0, right, okay. So what are we saying here? Okay, choose m hat as M0 if rho is greater than A. if the received signal is greater than 0, right? So the threshold becomes 0. Okay. So what is this? If received value is positive, right, you are declaring that as S0. If rho value is negative, you are declaring that as S1. Isn't this the minimum distance rule? Okay. What is this? If rho is greater than 0, which basically the received signal will be close to S0. If rho is less than 0, the received signal is close to -1. That's essentially the minimum distance rule. Okay. And it is basically coming from the map rule. Okay. So that map rule is basically reducing to the minimum distance rule, which we looked at in our original demodulator discussion. Okay. And what we did not look at that discussion is basically the effect of this a priori probabilities. Okay. Right. I could show you this minimum distance rule very easily with this by taking this a priori probabilities same. Okay. But actually in this case also a priori probabilities are different. You will get a different threshold, but at the end of the day that is also a minimum distance rule with a different threshold. Okay. And that is what we are going to see now. Okay. So let us see this. Okay. So in this case, if P of M1 and M0 as what we have taken in this slide, the minimum, this threshold comes out to be 0.4236. Okay. Right. And you see this, the threshold is moving away from S0, right. Instead of now it has become minus 0.4236. Okay. So what is happening here, that the probability of transmitting S0 is greater than probability of transmitting S1. Okay. So you are giving more region to declare S1, okay, basically as the correct decision. Okay. So you look at this minus 0.4236. So it is the decision region has become here. Okay. The threshold has moved towards here. Okay. So if the decision region is basically moving towards the negative side, okay, there is a more chances of declaring the received signal as S0, right, because the decision region is moving towards the negative side. Okay. Correct. And why is that happening? Because probability of transmitting S0 is greater than probability of transmitting S1. Okay. So now what happens if probability of M0, S0 and probability of S1 are same? Okay. In that case, so this noise variance still remains same. Okay. See this, both of them have like equal heights, and where are they intersecting? We just did this exercise in the last slide also. They will intersect now at 0. Okay. Intersection threshold is 0. Okay. So this is basically what students normally do is they when we give them a question like this, they intuitively calculate this threshold. Okay, that if given a system like this binary system, okay, it is declare a value receive signal as basically S0 if it is greater than 0. Okay, otherwise declare it as S1. But that intuitive probability or that intuitive calculation of decision threshold is wrong because you have not incorporated the a priori probabilities. Okay, right. So that is another takeaway. But what are we saying here? When the a priori probabilities are same, the decision threshold is balanced. Okay, it is balanced between S0 and S1. Okay, in the last case, P of S1 was greater, P of S0 was greater. Right. Okay. So the decision region basically was moving towards the left. Okay. Now both of them are same. It has come somewhere in between. Okay. Right. So what is the next case? Okay. So both the probabilities are basically the same. Okay. Now and what have I done here is I have reduced the noise variance. Okay. So what happens in this case? You see this, what will this noise variance do? Okay, noise variance is basically reducing the width of the noise PDF. Okay, so we have lesser noise in the system. Okay, right? What does this tell? Okay, so if you transmit this symbol, okay, right, it will basically, so that what is the probability that it will basically move away from 0? Okay, what is the probability? This is that probability, right? Okay, why? Because what are you doing? You are adding this, you are transmitting this S0, okay, and you are adding noise to it. If the noise has a lesser variance, okay, there is a lesser probability that it will cross the threshold, right? Okay, R is equal to S plus N, okay. If the noise has lesser variance, okay, then with a lesser probability, this transmit signal will cross the threshold, and that's what you are seeing over here in this region. Right, right, if you sum this probability, okay, this is the probability basically wherein this S0 will cross the region, will cross this decision boundary and move towards S1, okay, right, and you see this probability is basically come down when compared with this case. Look at this. Right, and why is that happening? Because the noise variance is higher in this case, right, okay, correct. What is this probability? This is basically probability of error, okay. You transmitted this S0, okay, right, the noise has taken it cross the threshold and move it towards the left side, okay, and what is the probability of error? You basically sum this up, correct, and with sigma square is equal to 1, this is basically the probability of error, okay, when sigma square is equal to 0.31, this is the probability of error. You sum this up, okay. So the probability of error has reduced because the noise has reduced, okay, right. So intersection threshold still remains 0, okay, because we are not changing the a priori probabilities, okay. But what are we showing over here? The effect of noise on how this, like how it is going to affect the transmit signal, because noise has a lesser variance, which essentially means what? It has the received signal has a higher SNR, right, okay. So, and this gets reflected like this, wherein the probability of this S0 becoming S1 is only this, right, and similarly is the case with S1 becoming S0. This is the probability of error for this. Right, okay. Now, you further reduce the variance, 0.1, you see what happens. Look at this, because noise has further reduced, okay. So basically, like, this is the transmit point, okay, and you are adding this Gaussian noise, but the variance of the noise is low, okay. So what is it telling? Okay, that when you have a noise like this, what happens? How will your received symbols look like? Okay, this is BPSK. Right, if the noise is a lower variance, what will happen? You will receive points only in this range. They will move like this. Right? Okay, so they will move little because the noise variance is low. Correct? Okay, and that's what is shown you over here. Okay, like look at this is the error probability, they're close to 0, right? So whatever you are transmitting, you will be able to receive that signal with the very high probability. You will be able to correctly decode that signal. Okay, that's what this plot is telling you. Okay, we only look at the constellation plot, but this is another way of looking at it from noise perspective. When you add basically when you plot it with the Gaussian PDF. Okay, right? What is R is equal to S plus N? N is Gaussian, and that's what we are plotting over here, right? And we are plotting them for two different values of S. Okay, one is +1, other one is -1. Okay, right? So intersection threshold remains same, but this is the key point. Okay, that with very low probability, you are going to make an error at the receiver. Okay, then you further reduce it. Okay, right? You see this. Intersection threshold remains 0. Look at this. Whatever you transmit, that's what you are going to receive. Even here, so they'll move very little. They'll stay in this range. Because look at this. Okay, right? Because the noise variance has reduced. You're never going to make an error. Right? Okay. So This is a noise variance at which communication system would like to operate, okay, because you will not make errors, but that is not guaranteed, and that is why we have all this LDPC codes to help you out, wherein the noise is high, but you can, by sending parity bits, you can recover the correct signal, okay, right. So, this above thresholding based receiver, as I said, is called a hard decoding, because you are already declaring that the received signal is either +1 or -1. That is what we do, right. So, if it is, we did it for BPSK, right, same idea can be extended for QPSK also. Why? Because QPSK is BPSK on x-axis and BPSK on y-axis, okay. So, if it is a QPSK symbol, you look at, you do this hard thresholding for the real part of it, then you do the hard thresholding for the imaginary part of it, right, okay. So, same idea can be extended, okay, right. So, for other higher order modulation scheme, we will have to do a little bit of more homework, but the idea remains the same, okay, right. So, this was basically the hard decoding, and we basically threshold, and the threshold is, we can calculate it very easily, okay, right. And typically the a priori probabilities are same, okay, for any message signal they are same, but you should, if they are not same, you should be able to incorporate those probabilities in your decision, okay, because they change the decision threshold, right, okay. So, after studying this, what is left for us to understand is the soft decision values, okay. So, what happens here is, what is our map rule? Again we come back to this map rule, okay, and you will quickly see that it is, the soft decision is only basically rewriting it in a slightly different form, okay, and that is what I am going to show you. What is our map rule? Fine. What did we do for this hard decision decoding? We basically simplified this, okay, correct. And now, but at the end of the day, right, what is this? This is basically a probability, okay, right. There is also another probability, this is a correct, okay, and we compare, we calculate this probability, we set it equal, both of these probabilities to be equal, and then we come up with the threshold, correct, okay, and we use that threshold to declare whether the transmit bit was +1 or -1. If we do not do that, okay, right, if we basically stick to these probabilities, okay, right, and then feed these probabilities to the decoder, that is what is called the soft decision rule. Let us see that, okay. So, what are we saying here? So, earlier we set them equal, okay, right, and then we basically came up with a threshold. I am not doing that now, okay. What are we saying? I moved it over here, okay, right. Now, what is this? P of r, this is the PDF, okay, right. So, and then I have substituted this, okay. What am I saying here? Okay, what is this? I am not simplifying it, okay, right. So, what is coming on top? What is this? This is a probability that M0 was transmitted, and this is the probability that M1 was transmitted, okay, right. I am not thresholding that. Whatever probability I have basically calculated, I keep that probability as such, okay, and calculate its ratio, okay. Now, if I want to threshold this ratio, okay, so what will happen is, that will become my hard decision rule. How will that happen? If this ratio is greater than 1, what will the message signal be? Message signal is S0. If this is less than 1, the message signal will become S1, right, okay, because it is rewriting the same thing in a different form. But instead of thresholding this, what am I doing here? I will keep these probabilities as such, okay. And what is this? What is this? We do not threshold, but calculate the above probability, okay. And what is this? First of all, this is the likelihood, right, and this is the ratio of to likelihood, okay, correct. So, what can you call it as? This is likelihood ratio, okay. Now, there is an exponential coming over here. So, typically you can further simplify this by taking a log of it, okay, right. So, that ratio is called log likelihood ratio, okay. And what is that ratio? Log likelihood ratio, it is a ratio of two likelihoods scaled by the a priori probabilities, correct. If you want to simplify this, you can set these like a priori probabilities to same, they'll get cancelled. Okay, so what is happening here, in order to understand it better, the ratio of log likelihood ratios. Okay, you have the likelihood, you take the log of that and then you calculate a ratio. And what is that ratio? That ratio tells us what is the probability of S0 being transmitted divided by the probability of S1 being transmitted. Okay. So if you look at it, what are we doing now? We are calculating the ratios and feeding that ratio to the LDPC decoder, right? So at this stage, we have not decided ourselves whether the transmit bit was 0 or 1 or plus 1 or minus 1. Okay. We are only calculated the ratios. Okay. And then you can, how is it going to help the decoder? I will give you an example. And what is that example? As I just showed you, that what happens at the through this AWGN channel. Okay, right? That this is what you transmitted. Okay, noise basically moved it to other side. This is what is received. Okay, correct. Now if you threshold it, you have already moved it to minus 1. Correct. Okay, you have already pushed it towards the minus 1. You have declared it with so much of confidence that the transmit signal was minus 1. Okay, so the decoder will have to do lot of work to bring it back to plus 1 to correct this error, right? But instead of that, if I pass on this probability, right, which I am calculating here, probability of this bit being 0 or this bit being 1, okay, I only pass this ratio, I do not declare it, correct? And with those probabilities, it will be easier for the decoder to decide to make it, to push it towards the towards the actual transmit symbol and correct the error. Okay, because you have not pushed it, you have not thresholded it, you have just retained these probabilities, and these calculating the probability like this is shown to give you 2.5 dB of gain. Okay, you can improve the SNR, okay, by a factor of 2.5 dB. Okay, by only making this change. Okay, and actually, if it is you get with this kind of improvement, okay, you can, there is a 3 dB improvement in SNR. The UE can go twice the distance, okay, with this 3 dB SNR improvement from the base station. Okay, and that improvement is huge. Okay, but typically, what happens is that in any receiver, you never do the hard thresholding. You always calculate these log likelihood ratio and then feed it to the decoder, which makes the decoder life easier, and then it is able to give you that gain. Okay. So this brings us to the end of a discussion on the demodulator aspect. And what did we learn in this lecture and the last lecture was two things. One is that how does this actual hard decision decoding is a result of maximizing the A posterior probability. Okay. And how do you define this A posterior probability? This is the probability of a given bit being transmitted, of a probability of a bit being transmitted given that you have received some signal. Okay. Right. So you maximize that probability, and if that first leads to hard decision rule. But if you do not use that, if you simplify it like this, if you rewrite it like this, okay, you can calculate the ratio of the probabilities or the likelihoods. Okay. And those ratios, if you feed to the decoder directly, then that will give you a much better performance than when compared with the case when you are thresholding and then feeding it to the decoder. Okay. So I will stop here. Thank you.